In this video, we will continue discussing the calculus of polar curves, specifically calculating an enclosed area. So in this case, we're thinking that we have a polar curve r equals f of theta, and we have a theta value which is varying from alpha to beta. And what that would do for us, and there is a small stipulation that the difference between beta and alpha has to be less than 2 pi, so the curve's not repeating itself. But what that really gives us is kind of this almost pizza slice shaped area or region whose area we would like to find. And luckily there's a convenient formula for us to use. The formula is that the area is 1/2 the definite integral over how the theta values vary, and what we integrate is the square of the f of theta. So let's look at an example. Let's find the area of the region enclosed by r equals 2 plus cosine theta. And note that this curve, r equals 2 plus cosine theta, is a curve that we encountered in a previous example, and the curve is traced out as theta varies from 0 to 2 pi. So the value of that area would be the definite integral over how the theta values vary, 0 to 2 pi, and what we integrate is 1/2 the function of theta squared, so the r squared, 2 plus cosine theta squared d theta. And just for an observation, note that if we wanted to do something like maybe find just the area enclosed, say in this second quadrant, what we would do is integrate from pi over 2 to pi. So as you change around those theta values, you get these different pizza sliced shapes coming from the region. So let's go ahead and now evaluate this integral. So in terms of evaluating, the first thing that we are going to need to do is just simplify inside the integral. So 2 plus cosine theta squared would be 4 plus 2 times 2 cosine theta, so 4 cosine theta, plus cosine squared of theta. And this is going to be something that we will very frequently encounter with a cosine squared or sine squared that we are integrating. So let me recall for you the double angle formula for cosine that allows us to integrate this. So we have that cosine squared of theta is 1/2 the quantity 1 plus cosine of 2 theta. And similarly for future use, sine squared theta is 1/2 1 minus cosine of 2 theta. So rewriting our cosine squared theta piece, this is 1/2 the integral from 0 to 2 pi of 4 plus 4 cosine theta plus 1/2 plus another 1/2 cosine of 2 theta. So we have taken the 1/2 and distributed through, and both of those terms have replaced the cosine squared. So let's go ahead and anti-differentiate. We can go ahead and leave the 1/2 out front, and then inside the integral we have 4 plus 1/2 combines to be 9/2. Then we have, and I'm going to just distribute the 1/2 through, the integral from 0 to 2 pi of 4 cosine theta plus 1/2 the integral from 0 to 2 pi of 1/2 cosine 2 theta. And individually, each of these three integrals is very reasonable. So for the first integral, it's just a constant 9/2 integrated from 0 to 2 pi. So we take that constant 9/2 and we multiply by the length of the interval. For the second integral, because it's a cosine theta from 0 to 2 pi, that enclosed area is going to be 0. So note if you have the integral from 0 to 2 pi of cosine or 0 to 2 pi of sine, that will always be 0. Plus in this third integral, let's pull the 1/2 out. So we'll have 1/2 times 1/2. And then the antiderivative of cosine 2 theta would be another 1/2 sine of 2 theta. And we need to evaluate from 0 to 2 pi. So we get 9 pi over 2 from our first term, plus 0 from the second term, plus we would have 1/8 sine of 4 pi minus sine of 0. And note, sine of 4 pi is 0 and sine of 0 is 0. So the only non-zero number that we have is 9 pi over 2, which represents the area of that enclosed region.